Okay, hi everyone. So this is going to be the second batch of lessons that I'm filming. We've spent 3 lessons now on stuff to do with gravitational fields. We looked at gravitational forces, gravitational field strength, and some stuff on work and gravitational potential energy stuff involving graphs. You should know that. It was only like, Monday, when you should have been watching the last videos, although it's been like a month for me since I filmed them, so that's why, whatever. We're looking at the last thing to do with gravitational fields today. That's going to be satellite motion. After this, we're going to be moving on to electric and magnetic fields, but this is the last thing we're looking at for gravitational fields, so we're still using those concepts when we work through this sort of stuff. I'm using the TV setup. I was hoping to do it on a PowerPoint, well, not on a PowerPoint, but on a projector, but the problem was that you couldn't see the screen when you tried using the iPad to film, so that's kind of out the window. So hopefully the setup works. Hopefully it's a bit easier to read than the stuff that I was doing, writing notes on the whiteboard. I'm hoping this works out, and if it doesn't, we'll have to try something else. But anyway, computer's over there, not the best location for it, but it is where it is. Okay. So satellites. A satellite is an object in a stable orbit around another object. Satellite is constantly flying towards the object that is orbiting, and the object's surface curves away beneath the satellite so that the satellite nave hits the surface. Should say never. Now, I'm going to put up a bit of a thing explaining exactly how this works. So we're talking about satellites. We're talking about one thing orbiting around another. And I've got up an example here where we've got a cannon at the top of the Earth, at the top of a mountain. The cannon shoots a projectile, and the projectile is going to move around. Now, hopefully, this is going to be visible to people because, like I said, the filming isn't perfect. If it's not visible, then I'm going to be describing it anyway, and you'll be able to get the gist of what's going on in the picture. So I'm starting out with it. Is that still visible? Cool. I'm starting out with it moving at 3,000 meters per second, which is a fast cannonball. I fire it, and it lands down there. It does exactly what you'd expect it to. It just goes off, hits the ground. Nothing particularly strange about that. So then if I step up the speed a bit from 3,000 to say 5,000, it's going down there, around to there. Nothing too weird. Step it up to about, let's say, 6,000. Now what's happening is it's going down to about here. So I'm tracing out the trajectory, starts there, goes down to there. What's happening is that if this was a flat surface, if it was like infinitely flat, then the projectile, if the surface was going along to there, would stop at about there, hit the ground. But because the surface is curved, as the projectile falls, it's moving fast enough that the surface is curving away beneath it. So whereas the projectile on a flat surface would only get to about there and then hit the ground, because the surface is curving away, what's happening is that the projectile can travel a bit further because the surface is moving away underneath the projectile as the projectile moves, so it gets a bit more distance to it. Now if I step this up to say 6,700, click on fire, it moves around to there, and it gets around to about a quarter of the way along. So what's happened is that the Earth is curving away beneath it to such a substantial degree that it's getting a lot more distance than otherwise would. Like I said, if it was just a flat surface, it would get to here and then stop. It's moving really far, but it's still not moving fast enough that it can avoid hitting the surface. Now if I finally get this to about, I think 7,500 is the magic number, and I click on fire, might even be too magic, you can see that what's happening is that it is moving, it's moving around, hopefully you can see it, if not you're just following my finger, it's moving around and it's ending up back where it started. So what's happening is that it's falling towards the Earth constantly, it's a constant state of falling, but as it falls, the Earth is curving away beneath the projectile at a rate that prevents the projectile from ever hitting the surface. So it's moving around a full circle. It's falling as it does so. The only reason it doesn't hit the surface is because it's moving at such a speed that the surface curves away faster than the projectile is falling. As a result, the projectile never hits the surface. So if you've got higher speeds, then it's just going to go further out and you get the same thing, so I won't bother doing those. So when we're talking about satellites, Whoa, what's going on there? When we're talking about satellites, we're talking about things that are falling towards whatever it is that they are orbiting. No, that's not going to work. So that's an important thing to keep in mind. We're talking about satellites. We're talking about falling objects that are getting pulled down towards somebody by gravity. But because they're moving at such a high speed, they're not going to hit the surface of that, whatever they're orbiting. So it's worth keeping in mind when I did that simulation with the cannonball up on the mountain that you might think to yourself, well, surely that wouldn't actually happen in reality because there's air resistance that's going to slow the projectile down, and so the satellite's eventually going to slow down, it's going to lose some of its speed, and it's going to end up hitting the surface. And that's going to be true if you launch something on Earth where you've got air that's going to impede the projectile's motion. But if you're up in space where you've got satellites, then there's no air up there. There's no air resistance to slow down the satellite's motion. So in theory, it can just keep orbiting around whatever it's orbiting the Earth for as long as it wants, just because there's nothing slowing it down. It's constantly falling at a speed that's fast enough to stop it hitting the surface. Because there's no air resistance, it's just going to keep going. It's not going to need any boosts or anything because there's nothing to resist its motion. Now, if you could see that image clearly, the projectile that I had up before, you would have seen that it was circular motion. When we've looked at circular motion, we know a few things about circular motion. We know that something's moving around in a circle, and the time it takes to go around the circle once is what we call the period. We also know that when we talk about circular motion, we've got the radius from the center of rotation out to the projectile. So the distance from the center of the Earth out to however far out the projectile is, that's another quantity that we can associate with the circular motion of the projectile. Just again, I'm using a swivel thing that moves around as I teach, so hopefully you can still see things. There's nothing being cut off on the side of the screen, but it's hard to tell while you're filming. So that's what we talk about when we talk about satellites. Now, going back a step, we've looked at something called apparent weight, and we looked at how apparent weight is just a measure of the normal force pushing on an object. And if something's in free fall, if it's falling down, it's not going to have any normal force pushing on it. It's going to be experiencing something called apparent weightlessness, where the normal force on it is zero, so its apparent weight is going to be zero. So it's going to feel as though it's got no weight. And this kind of ties in with what we were looking at on the last slide, because when something's in satellite motion, it's going to be constantly falling. So if someone's on a satellite that's orbiting the Earth, because they're constantly falling, they're going to experience something called apparent weightlessness. They're going to feel like they're floating because there's no normal force pushing up on them. So apparent weightlessness occurs when an object is in free fall. If it wasn't for any air resistance, you would feel as though you were floating when you were falling. So when you're falling down, you can tell that you're falling because there's air pushing against you. If you were in space and there was no air to do that, then you would feel as though you were floating even though you were in fact falling. So when we talk about orbital motion, some people think, well, the satellite is up there floating in space. Floating is about normally buoyancy pushing something up, and obviously there's nothing going on like that in space. When you're up in space, you're not so much floating as you are falling. You feel as though you are floating because there's no normal force pushing up on you, so you've got apparent weightlessness. Now, we distinguish between apparent weightlessness and true weightlessness. True weightlessness basically means there's no weight force pulling on you. And you know that you've got F equals mg, that's your weight force. So in order to get a weight force of zero, you need to have a gravitational field strength of zero. And that's only going to occur out in very deep space where there's nothing nearby to pull on you, no planets or stars. If that's the case, there can be a gravitational field strength of zero, and in that case you can have true weightlessness, but we're looking at apparent weightlessness. It's like weightlessness, it's like you have no weight. That's not in fact true, it's just how you feel because there's no normal force pushing up on you. So just important definitions to keep in mind. You definitely want to come back to this at the end of the year when you have your exam probably, because this is something that's easy to forget and something that examiners love to include on the exam. So just being able to explain the difference between true weightlessness and apparent weightlessness, being able to explain someone is in free fall, as a result there's no normal force, as a result they have an apparent weight of 0. That's something that you're going to need to do throughout the year. So moving on. Now, when we talk about satellites, we distinguish between two different types of orbit. We've got one kind, which is called geostationary, you've got the convenient diagram down here, and one called geosynchronous. And as part of Year 12 physics, we're concerned about geostationary orbits. We do different analyses of their properties. Geosynchronous, not so much, but geosynchronous is a term that you might have heard before. It pops up a lot when you talk about satellites. We don't look into those in a great deal, but again, it's just important to know the difference between them, to know what a geostationary orbit is, and to help understand that, it's good to be able to contrast it with what a geosynchronous orbit happens to be. So in a geostationary orbit, a satellite is going to remain above the equator of the Earth. You can see that your geostationary orbit, can you see that? I hope so. Your geostationary orbit on there is just about the equator. It's always going to be above the equator, and it's going to rotate the satellite with the same period as the Earth. As a result of those two things, being above the equator and rotating with the same period as the Earth, taking 24 hours to go around once, what you get as a result is that the satellite is going to remain in position above just one spot on the Earth. So if there's, I'm not exactly 100% familiar with my South American countries, I'm going to guess that this is Brazil over here. So if I'm wrong. So if a satellite is above this point in Brazil and it's in geostationary orbit, what that means is that 12 hours later, 10 hours later, it's going to be above that exact same position on Brazil. It's going to be positioned exactly above. It has to be on the equator, has to be set up so that it rotates with the same period as the Earth, but if you get that set up right, it remains stationary, and that's going to be useful for things like telecommunications satellites, right? If you know that there's a satellite that you can bounce a signal off that's constantly going to be up there, then that's something that you can make use of with something like telecommunications. So it's a good way to set up a satellite for certain applications. Geosynchronous orbits, the satellite does not stay above the same point, but passes over the same point once every 24 hours. So it's in the name, it's geo relating to the Earth, and synchronous in that it synchronizes up. It's not stationary above a single point like a geostationary satellite. It doesn't have to be above the equator. It can fly around at one of these angles, and as a result of that, you're not going to have it above the same points constantly, but it's just synchronized to pass over the same point periodically. So people get applications out of that. They set up satellites that way and make use of those. Just need to know that when we're talking about geostationary satellite, we're talking about this kind above the equator with a given period. Geosynchronous, depending on the angle that you set it up at, or depending on how far out you want to go. I don't think the period needs to be the same as the Earth. Don't quote me on that. But like I said, we're not so concerned with geosynchronous. We're much more concerned with geostationary. So this is kind of a long lesson with not that many questions, or the questions are reasonably short based around it. We're going to look at 3 things to do with satellite motion. They're called Kepler's 3 laws of motion. Now, the first law is that all planets move around the sun in elliptical orbits which have the sun as one of their foci. That second point, not so important, but I can see on the video that you can see that this is not completely a circle. The sun isn't sitting directly in the middle the way you'd expect it to be, the way it's traditionally drawn. Things move around in orbital motions in elliptical paths. Now, there's a bit of diciness when it comes to this stuff in Year 12 physics, because when you're asked to draw an orbit, you generally draw it as an ellipse. When you're asked to analyze motion, you generally assume that this is going to be a circle. So the equations of motion that we're going to be using are going to be built around analyzing this as being circular motion. It's not actually circular motion, it's going to be elliptical motion, and that causes the equations to get modified in a way that makes them more difficult. So when we do an analysis later on, of different things to do with orbital motion, we do treat this as a circle, even though it is in fact going to be an ellipse. So just keep that in mind. This is Kepler's first law. That's what it states. But we don't always do things consistently with that fact when we do satellite motion. The second one's probably the hardest one to get a handle on. It says that, well, I'll read the definition up here. Second law, a radius vector joining any planet to the sun sweeps out equal areas in equal lengths of time. So let's say we are here. The satellite starts here. A month later, it ends up here. If we have a line connecting the satellite to the sun and then another line connecting up the sun to where the satellite ends up, it's going to sweep out this much area within that month. Within the space of a different month, if it starts out here, it's going to end up there. It's going to sweep out within the month the exact same area. This area and that area should be exactly the same as each other. You're just going to have to, I guess, take my word on that. So the point is that when it's further away from the sun, it's going to move less far in a certain time compared to when it is closer into the sun. And if you think about conservation of energy, that doesn't seem that strange really, because it's got the same energy out here as it has in here. It's got a lot of gravitational potential energy out here, and it's got less gravitational potential energy in there because, well, when you think of gravitational potential energy, we've been doing the graph stuff, but the fact is that the further from an object you happen to be, the more gravitational potential energy you tend to get. The gravitational field strength gets weaker, but the distance gets bigger. So just thinking about your mgh for gravitational potential energy, it has more out here than it does in there. Because the energy at these two locations has to be the same, what you get as a result is it's got less kinetic energy out here than it does in here. Here it's got high kinetic energy, so it's going to move faster. So it's going to get from there to there in the course of a month. Less kinetic energy out here, moving more slowly. It's going to take a month to get from there to there, a smaller distance than the distance in there. So I think that's the main gist of Kepler's second law when you use it in year 12. It's stuff to do with your conservation of energy, stuff to do with how it's going to be moving slower when a satellite is further away from the thing that it happens to be orbiting. Now, the last law, I don't think I've put in a snazzy picture, but I'd call it the most important one that we have. Hopefully you can see on there okay. Kepler's third law, for every satellite orbiting the same object, the ratio of r cubed over t squared is the same. The ratio of the radius of orbit cubed divided by the period squared is going to be the same for two objects, satellites orbiting the same object. So here I've got a table, and I like this a lot. It's the planets, including Pluto. I didn't want to take that one off by cropping it out, but it's kind of consistent with the others, even though it probably shouldn't be on the list. It's got the periods in years. It's got the distance in units that are called AU. The way AU works is that the Earth is set to be 1 AU from the Sun. So all these distances from the Sun are basically relative to the Earth. You can see that this one's Jupiter, basically 5.2 times the distance of Earth from the Sun. That's just astronomical units. That's what AU stands for, and we use them when we're talking about planets and where they're located. Periods are in years as well. So here, rather than having r cubed over t squared, we've got t squared over r cubed. That's not going to make much of a difference for this analysis. You can see that if you do period squared divided by radius squared, you get 0.98, 1.01, 1, 1.01, 0.99, and then 1s for the rest of it. So these planets are all orbiting the same object. They're all orbiting the Sun. Because they're all orbiting the same object, the ratio of r cubed to t squared, or if you flip it, t squared over r cubed, should be the same. This ratio should be the same for all the planets. And that's what you find, that when you do those calculations from these numbers, square this, cube that, squared divided by cubed, you get out very closely the same number. A bit different for Mercury, but still very, very close to each other. So the ratio remains the same for all these objects because they're all orbiting the same body, the Sun. Now, up here I'm going to be doing some calculations, and that looks like you can see it all right. Sorry that I'm being strange around this. I just don't want to film a whole video and then have it turn out that you can't really see it properly. I've got up here some circular motion equations. Like I said, we analyze orbital motion as being circular motion, even though according to Kepler's first law, it's actually elliptical motion. So I've got your standard v equals 2 pi r divided by the period. Just remembering that this is the circumference of a circle, this is the period, how long it takes for the satellite to go around in one single cycle. So the speed is just going to be the distance it travels, the circumference of the circle, divided by the period, the time it takes to travel that distance. Just reminding you, this is stuff you've seen before. We've got some equations for acceleration for objects in circular motion. So the acceleration is v squared divided by r. We can substitute this for v squared into the v up the top, and we get out this equation as a result. And a reminder that when something is in satellite motion, it's in free fall. The only force acting on it is going to be gravity. So as a result, the acceleration of the object is going to be equal, the centripetal acceleration is going to be equal to the gravitational field strength at that point away from the object. So however high up a satellite happens to be, if you know the gravitational field strength at that location, you also happen to know what the acceleration of the object would happen to be, the centripetal acceleration. Remembering that it's moving at, if we assume it's moving in circular motion, it's moving at a constant speed, but it's still experiencing some acceleration because circular motion means it's changing direction. That means a changing velocity. Because we've got a changing velocity, we've got some acceleration there. So just reminding you, that's what the acceleration means when we're talking about satellite motion. Now, two equations, these two here, next to each other. The gravitational force acting on the object, the satellite, is going to be its mass times its acceleration. I take this term for acceleration, I put it in there, multiply it by mass, and I get this out. I'm going to leave that sitting there for a bit. We've also got gravitational force is going to be mass times gravitational field strength. Gravitational field strength is your gm over r squared. I times that by the mass of the satellite and get out this term here. Now this Fg and that Fg have to be equal to each other. So I'm going to set those two things equal, this and that. I'm going to cancel out the little m's, the mass of the satellite. So these two disappear, and I get this equation here. I do some rearrangement because there's an r there and an r squared there, and I get out this equation, and this looks like what I had up on the board before, up on the TV. I've got r cubed divided by t squared, radius cubed divided by period squared, equals gm over 4 pi squared. And I put in a whole bunch of arrows because I feel like this is the biggest equation on the court as part of Year 12 physics. Every single year there's a question on the exam that gets awarded a hefty number of marks, like 3 or 4, and it basically boils down to, can you use this equation to answer a question that's actually not particularly tough? And the reason a lot of people get caught off guard is that every year this equation is not on the formula sheet that you get. You can of course take it in with you to the exam, but I just better check I'm not running out of recording time. Let's see, whatever, I'll survive if I don't. But this equation, you can derive it like I've done from scratch, which you don't want to do during an exam because you're under limited time, but you can derive it from equations that are on your formula sheet. I think they give you some stuff that you could use to get to this point. But the point is, please 100% make sure that this is on the formula sheet that you take in with you to the exam. Make sure you know what everything means. Make sure you know what all the constants are. G is the gravitational constant. I think that's 6.67 times 10 to the negative 11. M is the mass of the object that is being orbited. So using my example from earlier, I had the planets and their periods and their radiuses. And if I wanted to calculate this ratio without knowing those numbers, if I wanted to know what this was equal to, I'd use these numbers here, with m being the mass of the sun, the object that is being orbited. So if I'm talking about the Earth orbiting the sun, well, the sun is the object being orbited. I would use that as the mass in this equation. If I was talking about a satellite orbiting the Earth, so a natural satellite like the moon, or an artificial satellite like a satellite, can't think of a better word for that, then I would use the mass of the Earth in this equation here. So just keep that in mind. Big M, little m's up here with the mass of the satellites, and they cancel it out. We don't need to know those to do this kind of analysis. Big M is just going to be the mass of whatever is being orbited. So just keep that in mind. If they give you two masses, they say here's the mass of the Earth and here's the mass of a satellite orbiting it, calculate r cubed over t squared. You can ignore the mass of the satellite. You're just interested in the mass of the object that is being orbited, the mass of the Earth in that situation. So I'm going to do two examples using that equation. They're pretty much the same example, but it's worth doing both. I'm hoping that you can see those. I'm up the creek. If you can't, I could always just upload the PowerPoint and you can watch along from home. So I guess I can be flexible on that front. But example 1, a satellite is orbiting the Earth with a period of 48 hours. What is its orbital radius? What is the orbital radius of this satellite? So first of all, I need to have standard units. This tells me that the period is in hours. I take the hours and I times that by 60 to get how many minutes I've got. I take those minutes and I times them by 60 again, 60 minutes in an hour, 60 seconds in a minute, and that gets me this number of seconds. I'm assuming I did that correctly, who knows? I'm concerned now that I didn't, but whatever, life will move on. So I've got my equation, r cubed over t squared. Now, that's always going to be the equation that I use to link together radius, or I've called orbital radius in this situation, just to illustrate that it is how far something away is from the center of the body that it's orbiting. When we talked about stuff to do with gravitational field strength, we said, well, something has a radius and then something is so far above the surface of whatever planet it's orbiting. Here, orbital radius is just how far something happens to be from the center of the object that's orbiting. So if something's in circular motion, it's got a certain radius from the center of the thing that's orbiting. That's just what we can call the orbital radius. So I've got my equation. This is the one that links my period of 48 hours with my orbital radius that I'm after. I kind of cheated on this question and I didn't write up the mass of the Earth. I believe that's on the formula sheet that you get as part of the exam. So just keep that in mind. It's 6 times 10 to the 24 kilograms. It's just something I know off the top of my head. Something that's convenient to just remember. It's something like that. When you do an exam, you can be like, have I got the right number? And if you know that it's something that looks like that, then that helps you verify whether or not you've somehow picked out the wrong number to use, whatever. I could have just written that up there at the top, but I chose not to. So I substituted my numbers. I've got my r cubed, I've got my t squared. I need to remember to square that. It's very easy to just plug in this number and go, oh, it's a big number, and so I'm not going to square that. And then you leave off a factor of 172,000-ish. And then your answer goes all skew-if. But I've got my g, my gravitational constant, 6.67 times 10 to the negative 11, mass of the Earth, 6 times 10 to the 24 kilograms, divided by my 4 pi squared. I remember to square the pi. That's another way that you can easily go wrong if you leave off that factor there. I do some rearrangements, times both sides by the denominator of that fraction, and I get this out. I calculate that this is 3.027 times 10 to the 23. I take my cubed root of this and get out my answer of 6.71 times 10 to the 7 meters. That fortunately is not located within the Earth. It would be a bit of a problem if I got out that it had an orbital radius of, say, 10 to the 4 meters. I know that the Earth has a radius of something like 10 to the 6, something on that order. So I can just verify whether my answer makes sense by saying, is this going to be reasonable? Is it going to be within the Earth? Is it going to be like crashing into the sun because it's so far away because this is such a large number? That's just a good check that you should do with your answers to make sure that they make sense, because if they don't, it's probably not going to be correct. Now, a bit of a side note, if you've got those green calculators, you can get cubed roots on those, but a lot of people forget how to do that. I've written it up there on the board how you go about doing that, but at the same time, I can just show you. That's the wonderful thing about film. So you can just press the 3 button, 3, and then you press second, and then the little up button, and that's going to get you a cubed root. It looks like, oh my god, how does this work? Looks like that. If you're on classic mode, if you're on maths print, then you should reconsider the choices that you've made in life, because maths print is not the way to set a calculator when you're doing physics. But those are the instructions. You just type in cubed root of, if I want to cube root of 27, I just type in 27 after that. Yep. Yeah, it's inverted, it's bothersome. But That's how you do a cubed root, just in case you've got a calculator like this one and this is something you'd need to know for a question like this. That's the approach that you'd use. It's very easy to get to the end of a question like this and go, crap, how do I do a cubed root? There's a square root button but not a cubed root button. Just keep that in mind, that for that calculator, that's what you'd use. If you're using a different kind of calculator, I guess you're on your own. You've got to figure it out. Ask me if you're not quite sure how to do it. And send through a picture of your calculator so I can actually see what's on it. Example 2, pretty much exactly the same. A satellite is orbiting the Earth at an orbital radius of 9 times 10 to the 6 meters. Again, good distance, not inside the Earth, not the moon, not so far away that you'd think it would be the moon. Was the period of this satellite. So I start with my exact same equation. It's orbiting the Earth, and I know the mass of the Earth, and normally be provided with the mass of the thing that's being orbited, so that's a bit of information that you know is going to be needed to link your variables together. You've got the orbital radius, 9 times 10 to the 6, so I plug that into the top. I've got my other stuff, which is exactly the same. It's still orbiting the Earth, so this is a factor that's not going to change. I then need to do some rearrangement, and the only reason that this question's harder than the first one is that the thing that we want to find is in the denominator of the fraction. So some people struggle with, you've got it in the denominator, how do you rearrange the equation to get the thing on its own? I like to just times both sides by t squared, so there'd be a t squared over here. Then we just times both sides by 4 pi squared and divide both sides by the numerator of this equation. So the 4 pi squared would go up there, this would go down there, and the t squared that I moved over here a moment ago would just be on its own. So we've got this, we put it into a calculator and get that, we do a calculation and get it in seconds. If the question was asking for how many hours or how many days is the period of the satellite, you'd need to do some kind of equation, divide it by 60 to make it into minutes, divide it into 60 by making it into hours, divide by 24 to make it into days, to convert the period into something like that. And I believe that was the last slide. It's hard to tell with things like this. Yeah. So what you're doing today is you're working from chapter 3.1. I'm using my textbook to prop up the thing because otherwise it's angled weirdly. So unfortunately I can't look at it right now. So you're doing the questions from 3.1. That's all on satellite motion. But again, the question plan is up on Compass. It's just called like Field's question plan, I think. So if you're unsure of exactly which questions you should be doing, please go onto Compass and download that. I hope you have already, but if you haven't, please do that. Also, remember that you need to be doing those Ed Rollo questions. They are what I'm using to assess whether people are staying up to date as part of the course, and if I see that people aren't doing those, I'm going to start worrying that you're not following along with the videos and you're not doing the textbook questions. I know some other teachers are getting students to upload scanned or photographed images of their work to Compass, and there's value in that, and if people aren't doing the Ed Rollo stuff, I might move over to doing that. But for now, I think you should just be doing your textbook questions and your Ed Rollo questions. This is a weird thing to say because if you're listening to this, then you're watching the video, and so you're probably not someone who I need to complain about not watching the video. But for some reason, some of the videos only have 3 views, and there are 4 students, and that gets me worried. So I don't know. We'll have to see. But anyway, you're doing chapter 3.1 for today, and that is it from me.